Hello and welcome to this lesson on the Mass Spectrometer. It has specification reference 3.1.1.2 and the lesson objectives that we're going to study are as follows. So first of all, we want to know that the Mass Spectrometer gives accurate information about relative isotopic mass and also about relative abundance of those isotopes. So just to clarify, if we have a relative isotopic mass and we have the abundance of those isotopes in a sample, we combine those two, and what we're going to get is we're going to get the relative molecular atomic mass, or the relative molecular mass if we're dealing with molecules. They're the two components of relative atomic mass. So then after that we will understand the principles of a particular type of mass spectrometer, and the mass spectrometer that is in your spec is the time of flight mass spectrometer. So time of flight is the way that you separate the different isotopes. So heavier ones are going to take longer to get across the mass spectrometer than lighter isotopes, and so you can use that time of the isotope to get from one end to the other of the mass spectrometer to differentiate between the isotopes. Okay, once we've looked at the mass spectrometer, we're going to look at what comes out of the mass spectrometer, and you get spectra out of the mass spectrometer. So your spectra might look something like this, right, where each of those vertical bars on the graph is for a particular mass to charge ratio of an ion of an isotope, and the height of the bars is going to be the relative abundance of those isotopes. So we're going to interpret the spectra such as that one, and lastly we are going to know how to identify elements using mass spectrometry. So if the first lesson objective up here was what to do with the mass spectrometer, the first thing we'd want to do with the mass spectrometer, i.e. find relative atomic masses, for example, the second thing that we can do with a mass spectrometer is identify elements with them. So if you know the spectra of each element, but you don't know the element, then of course you can put the element into a mass spectrometer, get a spectra and match it to all your known spectra, and then find out what element you've got. So there we are. Let's crack on then. And first of all, I just thought I'd show you a picture of a real mass spectrometer, because when we deal with the diagram, when we go through the steps of how it works, it's necessarily simplified. But this is what a mass spectrometer might look like in practice. You can't see much because all the action's going on inside, but there we are. And let's have a look at an actual diagram schematic of a mass spectrometer. Yes, here we have the schematic of a mass spectrometer, and I'd like to draw your attention first to the first chamber on the left, which is where electrospray ionization happens. So let me just label that electrospray ionization. So this is a nozzle on the left, and so the product that you're investigating is squirted into this first chamber through the nozzle, and it's been dissolved in a polar solvent, and it comes in at high pressure. Now in this chamber, what you do is you apply a high voltage to your sample, and that causes these particles to lose an electron and therefore become positive ions. And so in this case, you can see we've got blue ones, and we've got let's call that red. We've got red ones, and they represent the two different isotopes, and they're now positively charged ions. So let's move on to the second chamber. Let me label it for you. This is where acceleration happens. in the second chamber, and the acceleration happens because we apply an electric field to these ions. And so we're accelerating them from left to right. And the same amount of force is applied to each of the particles. But and so each particle gets the same amount of kinetic energy. And you might remember that from physics, that kinetic energy equals half mv squared. And in chemistry, you don't need to know that formula for kinetic energy. Suffice to say for chemistry that if m is bigger, then v is going to be smaller. And in v is going to be smaller because each of the particles is given the same amount of kinetic energy. So they're accelerated from left to right as you look at this diagram, and you notice the two holes in the electric field grid. And what they do is they just make the particles travel in a straight line from left to right towards the ion detector, as you'll see on the right hand side. So they stream through the right hand gap. That's what I'll make a little arrow here. So they stream through there. And by the time they get through that gap, they're no longer accelerated, and they're now going at the speed that they accelerated to. And so the next chamber, the big third chamber there, is called the ion drift chamber. So they travel from left to right at the speed that they reached by the time they left the second field. And you can see the blue ones have, in the same amount of time, have traveled less far than the red ones. So that's because they have a higher mass. So if they've got a higher mass but the same kinetic energy, then they're going to have a lower velocity. Whereas the little pink ones have traveled further along the middle chamber from left to right because they have a lower mass to charge ratio. Let's say the charge is both 1 positive, then the amount of time that it takes them to get from left to right just depends on their mass. So the smaller or less massive particles travel across that main chamber in less time than the heavier ones, the ones with higher mass. So let's just finish off that little chamber by labeling it. This is the ion drift chamber. And lastly, we have the detection chamber. So let me just label that for you. This is the detection chamber. And what happens is an ion, which is obviously charged, hits the detector and creates a little pulse of current. And so the amount of current that's produced is proportional to the amount of ions that hit the detector. So for each ion, it can work out the abundance of that ion because that'd be proportional to the current that's created when those ions hit the detector. And it also calculates the time, also measures the time that it's taken to get to the detector. So then it can use those two bits of information to create a spectra, which we will see in a couple of slides' time. But for now, what I want to do is I just want to show you a little moving animation of a mass spectrometer. It's only about 15 or 16 seconds long, but what's going to happen is that in a real machine, you've got the nozzle at an angle to the actual ion drift and electric field chambers. But you'll see if you look carefully, you'll see a sample being injected in, and there will be an electric field applied to that, and so you'll have different coloured particles travelling vertically up the screen in the machine, and they'll be reflected off the top of the machine to a detector at the bottom of the machine. And so what it will do then is you'll see the different isotopes being separated by the electric field. You'll see them travelling at different speeds through the ion drift chamber, and then you'll see them hitting a detector, and last of all you'll see the machine, the computer part of the machine, just making a little simple spectrum for you. So hopefully from the previous little animation you saw the spectrum that was produced at the end, and it looked something like this. It had a y-axis which is equivalent to percent abundance. And that gives you the height of the line, and along the x-axis on that spectrum was time, because it's a time of flight mass spectrometer, but time is proportional to your mass charge ratio. So you can just label this as mass charge ratio, because a computer can very simply convert between time and mass charge ratio, so you don't need to list time. And so for each isotope, let's change color. For each isotope, you notice that you're going to get different heights. So each bar represents a different isotope, and the height of that isotope is given by the abundance. And in that animation, hopefully you noticed it was the smaller particles, the little smaller spheres, that went through the chamber fastest, and the larger, more massive spheres took longer to go through the chart, and the lines were drawn in that order. So usually the charge here is a 1+ charge, and so what you can do is usually assume that because all the charges are the same, they're just 1+, that the mass charge ratio is equivalent to the mass of the isotope. So you might, for example, have 35, 36, 37, 38 for 4 different isotopes of a molecule, say, and you would then be able to work out from the height of these bars the percent abundance of each one, and then you do a weighted average on each one and get from that the relative molecular mass. So let's now have a look at a real mass spectrum. Here we have one here. This is for chlorine, and what you can see straight away is that there are 2 peaks. 2 peaks, 1 and 2. So that means we've got 2 isotopes of chlorine. So if we look at the first peak, we can see that the mass charge ratio of the first peak is 35. And what you'll note is that the ions have been given a 1+ charge. So 35, which is the mass, divided by 1, which is the charge, equals 35. And so you can say that for the first isotope, the relative isotopic mass is 35. I'm just going to switch to green to do the other one. So for the green one, we have the mass charge ratio for the second isotope is 37. And in the same way, the mass to charge ratio is 37 over 1, because they're both 1+ ions. And 37 over 1 is, of course, 37. So 37 is the relative isotopic mass of the second isotope. Okay, so that's that. Now the next thing to notice is that the height of the peak, let's go back to the first isotope. So the height of the peak, I'll switch to blue, say, the height of the first peak, so we're going to read it off the graph here, and that as is labeled there, is 75 95.5% of your sample is isotope number 1, which has the relative isotopic mass of 35, and you read the abundance of the second isotope in the same way, and that gives you 24.5% is the amount in the sample of the second isotope. So from that you could do your weighted average and find the relative atomic mass of chlorine would be 0.755 times your 35 plus your 0.245 of your 37, and that would come out to about 35.5, which you see on your periodic table is the relative atomic mass of chlorine. So you might remember from the learning objectives that the second main use of mass spectrometers is to identify elements. So for example, let's say you've got a sample and you don't know what it is, you want to know what it is, so you put it in your mass spectrometer, and then what you might do is you might get a spectrum out of the mass spectrometer that looks like this. You still don't know what it is, but it knows that there was 79% of an isotope which had a mass charge ratio of 24. There's 10% of it had a mass charge ratio of 25, and 11% had a mass charge ratio of 26. So that's what the mass spectrometer would tell you, and then a computer connected to the mass spectrometer might easily just refer to a database with that information, and it would come up with the fact that magnesium, as it happens, has that sort of spectrum. When a sample of known magnesium was put through the mass spectrometer, that was they were the abundances of the 3 isotopes of magnesium. So you can see that just like fingerprints are unique to an individual human and therefore are used to identify humans, well, the mass spectrum is unique to an individual element, and so they can be used to identify different elements or different molecules, in fact, in exactly the same way. Okay, and lastly, as usual, let's make sure that we've covered off our learning outcomes. Firstly, we were to know that the mass spectrometer gives information about relative isotopic masses and also about the abundance of those isotopes. I think we did that, and we combined them to work out what relative atomic or molecular masses would be. So we can give ourselves a big red tick for the first one. Do we understand the principles of time-of-flight mass spectrometer? Well, we went through it chamber by chamber, and we saw a little animation of it as well to make it slightly more real. So we can tick that one too. Then we interpreted mass spectra of elements by means of a chart, and then we also looked at the information in the opposite way round to use the spectra to find out which elements we were dealing with. So we're all done. Hopefully that's been interesting and useful. I'll see you in the next video.